So here it is, putting all of this together. Why is this useful, right? All of this stuff that we're doing here. Well, one way that this particular technique and everything you've learned so far is important for chemists is because it allows them to determine the formula for a hydrocarbon. And hydrocarbons, of course, contain carbon, hydrogen, sometimes oxygen, sometimes nitrogen. And they can do that by reacting that compound with oxygen and looking at how much product they formed, which of course the products of that reaction are carbon dioxide and water. And they could figure out what's the formula by crunching a lot of numbers together. And that's what we're going to do here. So a common way for chemists to determine the empirical or molecular formula for a hydrocarbon is using combustion analysis. And in this process, oxygen reacts with the compound in question to drive off, which means it's producing water, carbon dioxide, and nitrogen. So remember, a hydrocarbon has some amount of carbons, some amount of hydrogens, and a lot of times some amount of oxygens as well. But generally, I'm just going to put C and H here. And combustion, of course, you're reacting that particular compound, whatever that hydrocarbon is, right? I didn't include oxygen, I didn't include nitrogen, but it could include those two. We're reacting it with oxygen. And the products of a combustion reaction are always carbon dioxide and water. So knowing how much carbon dioxide is produced and how much water is produced, we can figure out what is the empirical formula of the hydrocarbon. And that's what we're going to do in this particular example here. So, again, putting all of this together. A substance has been prepared in the lab. It's composed of the elements carbon, hydrogen, and nitrogen. Okay, so we got some nitrogen in there. When 0.1156 grams of this compound reacts with oxygen, 0.1638 grams of CO2 and 0.1676 grams of water are collected. So actually what we can do is let's write that out up here. So we have some compound, right? And I'm just going to do it up here because I have more room. We said it contains carbon, so I'll do X because we don't know what X is. We're trying to figure out what that is. It has some hydrogen, which we're going to make as the subscript Y. And I have some amount of nitrogen, which I'm going to make this as Z. Okay. That's my formula. I know it contains those three elements, but I don't know what X, Y, and Z are. That's what we're going to figure out. And it says that I reacted 0.1156 grams of this compound. So I had 0.1156 grams of this. And I'm reacting this with oxygen, okay, O2. Now there is nitrogen in there, but we're going to have some other products that we really don't care about, right? But two products always of a combustion reaction is CO2 and H2O. Now we're going to have a compound that contains nitrogen. So I'll just put plus something else because we're not sure what that is. And ultimately it doesn't matter. But it's also telling me 0.1638 grams of CO2 is produced. So 0.1638 grams of CO2 is produced. And I also produced 0.1676 grams of water. Okay. Here's how we could figure this out. We can determine what mass of carbon is present in the empirical or in this formula for this unknown compound because, check this out, let's use a different color. All of this carbon was converted to CO2. So if I know this mass of CO2 that was produced, I could figure out what percentage of that or what mass of that is just carbon, right? Because all of that carbon that was made into CO2 came from this. So I could figure out how many grams of carbon are in the initial compound. Let me show you how to do that down here. So I'm going to start off with this. I know that we produced 0.1638 grams of CO2 was produced. Okay, I'm going to do a little bit of stoichiometry here. One down below. Grams, got to get rid of grams. When in doubt, mole it out. Molar mass is 44.01 grams of CO2 is equivalent to 1 mole of CO2. That cancels out grams to grams. What I can do at this point is, let's look at the mole ratio. So, okay, 1 mole of CO2 contains how many moles of carbon, right? And if I look at my formula for CO2, 1 mole of CO2 contains 1 mole of carbon because there's only 1 carbon in CO2, right? If I have 12 molecules of CO2, I have 12 carbon atoms. If I have 500 molecules of CO2, I have 500 atoms of carbon. Therefore, if I have 1 mole of CO2, I also have 1 mole of carbon. So, based on the fact that there is 1 carbon in 1 CO2, I can use that as a conversion factor, okay? So there is 1 mole of carbon and 1 mole of CO2. That cancels out. Now that I'm in moles of carbon, right, I could convert this to grams of carbon because I know 1 mole of carbon, you look at carbon's mass on the periodic table, it's 12.01. And when I solve for this, I should find that my answer is 0.04470 grams of carbon. So of this 0.1638 grams of CO2 that was produced, 0.04470 grams of that is carbon. And if 0.04470 grams of that sample is just carbon, that must mean that 0.04470 grams of this sample must contain that much carbon, because all of that carbon that was in the CO2 came from this unknown hydrocarbon. That's where we're going with this, right? So we know that this must be equal to the mass of the carbon in, see, I can't do this, in the hydrocarbon. Whatever, you can rewrite what I said there. That's the mass of carbon in the hydrocarbon, which is going to help us determine the empirical formula. And let's see, soon determine the mass and mass percent. So we determine the mass. So what percentage of that unknown hydrocarbon is carbon? Let's take that and go take the mass of carbon that we know is in that sample. And I have 0.1156 grams of the hydrocarbon. I'll just put HC for hydrocarbon times 100. We know that that initial hydrocarbon is 38.67% carbon. Okay, so there's our 2 answers right there. There is the mass of carbon, and there's the mass percent of carbon in the sample. Okay, so that one's done. Let's try the same thing for hydrogen, because if I look at my balanced chemical equation from up here again, all of this hydrogen in the hydrocarbon was converted to water. So I can determine of the mass of water, what mass of that comes from hydrogen, knowing that there are 2 atoms of hydrogen and 1 molecule of H2O. We're going to do this using stoichiometry. This is why stoichiometry is so important, because if you can, or why dimensional analysis is so important, if you can cancel out units, you could do anything in chemistry, just about anything. But man, if you got that dimensional analysis down and you could cancel out those units and you keep track of those units, that's half the battle in chemistry, really. So I'm gonna be a little strict with you guys about keeping these units here, because you gotta keep track of those. It's gonna help you so much more in the long run. Anyway, let's do hydrogen in the substance. So I know I produced 0.1676 grams of water. 0.1676 grams of water. Let's convert this to moles of water first. There's 18.02 grams of water in 1 mole of water. That's just a basic Chem 1 question. That cancels out. Now that I'm in moles of water, let's convert it to moles of hydrogen. So 1 mole of water molecules contains 2 moles of hydrogen, because there are 2 hydrogens per every 1 molecule, right? So in this case, my ratio is double. It's a 1-to-2 mole ratio. Moles of H2O cancel, so notice how we're really sticking to those units here. Whatever's up top, I'm going to bring down. Moles of hydrogen. I can convert that to grams of hydrogen, because 1 mole of hydrogen has a mass of 1.01 grams. I'm not making this a diatomic here, because I'm just focusing on how many hydrogens are there. We only deal with diatomic hydrogen if we're looking at a chemical reaction and I'm producing hydrogen. But in this case, because I'm counting the number of hydrogens, it's not H2. It's 2 moles of H. And when I solve for this, I'm left with grams of hydrogen, which is what I want. I have 0.01879 grams of hydrogen. So in 0.1676 grams of water, there is 0.01879 grams of hydrogen, because all of the hydrogen that came from this water that's in this water came from this hydrocarbon. That must mean that these 2 hydrogens have the same mass, right? So let's do green here. All this hydrogen that's in H2O came from here. So the masses have to be the same. So I'm going to say here again, equals mass of hydrogen in HC, hydrocarbon. So if I want to know what's the percentage of hydrogen in the hydrocarbon, I'm going to do the same thing I did up here. Let's take the mass of hydrogen in the hydrocarbon, which we just said is 0.01879 grams of hydrogen. Divide that by the total mass of that hydrocarbon, HC again, times 100. And I'm left with 16.25. There's everything I need for this one, right here. This is taking almost everything we've done in this unit so far and putting it all together in a very complex problem. And I don't think College Board actually assesses you on combustion analysis. They used to. So I like to keep it in there just in case. Plus, it is really good practice. There's a lot of stuff you have to understand why it works. Chemistry is not a memorization topic. You have to truly understand why everything is the way it is. So if you do not understand why I did something, please make a note and ask me the next time you see me, because chemistry is all about understanding in your soul why things work the way it works. So that's it for B. Determine the mass and mass percent of nitrogen, the remaining element in this compound. We know that this compound contains 3 elements. It contains carbon, it contains hydrogen, and it contains nitrogen. I already have, all right, the percentage of carbon, and I have the percentage of hydrogen. So I know that the total percents have to equal 100. So I'm going to go ahead and just do a little subtraction. So, all right, 100% is the total. I'm going to subtract 38.67% of carbon from that. And I'm going to subtract from that the 16.25% hydrogen. And when I do that, I get 45.08% nitrogen. So that's the mass percent of nitrogen. Question's asking, though, what's the mass and mass percent? We could do this the same exact way. We know that this compound contains 0.11, or that this compound is 0.1156 grams. We figured out that 0.04470 grams of that is carbon, and 0.01879 grams of that comes from hydrogen. So I'm going to do another subtraction and say, okay, well, what's the remaining mass? Because it has to be nitrogen, because there's only 3 elements that are in it. So let's do, and this is just 2 ways of doing the same exact thing. And we're only doing it this way because it's asking us to do this. Of the compound minus 0.04470 grams of that is carbon, minus 0.01879 grams of that is hydrogen, and I get that 0.05210 grams is nitrogen. These are the 2 values that this particular question was asking for. Using all of that, let's determine what's the formula for this compound. So lots of stuff going on here. We still don't know the formula for this compound, but now that we know a lot of this information, let's go ahead and determine, well, what is the formula? Because if I know the percents, I could easily figure out the empirical formula. So let's make 3 columns here. I don't have a lot of space. Hydrogen and nitrogen. I know the percents, so I'm just going to plug in the percents, but I'm going to change them right to grams. Remember, you can also use these masses here and just go with it that way. You should get the same exact answer. So let's see, 38.67, 38.67 grams, 16.25 grams, and 14.01 grams. I'm going to do this work. You could do the work and pause this video and see if you get the same answer as me. I'm just determining the empirical formula. So these are the values I got. Notice that I did make a mistake there. This should be 45.08. And actually, I still made that percent. Doesn't matter, but I'm just going to change that to grams there so we're consistent. I accidentally wrote 14.01 there the first time, just as the molar mass for nitrogen. Here's my values. I got 1.001, which is 1, very, very close. 5 hydrogens and 1 nitrogen. I don't have to multiply anything because I have all whole numbers, so that works out wonderfully. That's my empirical formula for this compound. And then it says, if the molecular mass of the substance is found to be 31.06 grams per mole, is the formula you calculated the empirical or the molecular formula? Let's go ahead and figure that out. The molar mass for this empirical formula happens to be 31.06. So in this case, the molar mass of the empirical formula is the same as that of the molecular formula. So, and it does say use a calculation. So I'm just going to show a calculation. I know it seems a little silly, but it is asking for that. And I want us to be aware of doing that throughout the year. Oops, not times, I meant to write equals. We want to be very thorough in how we answer these questions. I get 1. So in this case, because the molecular molar mass equals the empirical molar mass, the empirical and molecular formulas happen to be the same. So they are the same. They are the same. So in this case, CH5N is both the empirical formula and the molecular formula. And that's why combustion analysis can be, it's so important, is because it takes everything that we've done so far and allows chemists to do a reaction with some hydrocarbon based on the masses of the products. What is the formula of that hydrocarbon, right? This is a real life thing that chemists could do to figure out. Let's take all of this, and I broke this up section by section with sample problem 7. Let's go ahead and do this with sample problem 8. So we do have the whole page for this here. One of the additives in unleaded gasoline that replaced tetraethyl lead in leaded gasoline is called MTBE. When 15.078 grams of MTBE is burned completely, 37.640 grams of CO2 and 18.489 grams of H2O form. In a separate experiment, the molecular mass of MTBE is found to be 88.150. What is the molecular formula? It contains carbon, hydrogen, and oxygen. So let's get an equation down. I think that's important. So MTBE, we know it contains some amount of carbon, some amount of hydrogen, and some amount of oxygen. And I'm performing a combustion analysis, right? So I'm going to react this with O2. And I produce CO2 and H2O. And it gives me amounts of these as well. So when 15.078 grams of that reacts with oxygen, I produce 37.640 grams of CO2 and 18.489 grams of water. We want to know what's the molecular formula. Notice that there is oxygen in every single reactant and product here. So I cannot do what I just did up above with oxygen. And that's because the total mass of oxygen in CO2 is not equal to the total mass of oxygen in MTBE. And that's because I can't forget that there's oxygen here and here as well. So what we're going to do is, using that mass of CO2, we can use just carbon to say, all right, how much of carbon in MTBE comes from that CO2? Because there's only carbon in CO2 and there's only carbon in MTBE. And we can do hydrogen from water, because all of that hydrogen in MTBE was transferred into water. So I can only use that for each of those. Oxygen we're going to save for last. So let's keep this color coded here. So I'm going to do green first. Let's figure out what mass of carbon is in this sample. So of the 15.078 grams, what mass of that is carbon? I know I produced 37.640 grams of CO2. 37.640 grams of CO2. Let's convert this to grams of carbon. So, same thing as before. Molar mass, 44.01 is equal to 1 mole. 1 mole of CO2 contains 1 mole of carbon, because there's only 1 carbon in CO2. And 1 mole of carbon has a mass of 12.01 grams. All of these cancel out, right? Everything that's opposite. I know it's a pain in the neck, but I promise doing this dimensional analysis, canceling those units is going to make your life easier in the long run. 10.27 grams of carbon. So of this 15.078 grams of MTBE, 10.27 of that is carbon, right? And again, this technically belongs to how much of this is carbon and CO2, but because all of the carbon from here went into that, it's the same thing. Let's do the same thing for water. It's not asking us for a percent, and really I don't need to do a percent because you're making more work for yourself. Let's do the water sample here. So figure out how much hydrogen is in this sample. 18.489 grams of water was produced. Molar mass, 18.02 grams of water is equal to 1 mole. Cancels out. Now we have 1 mole of water. 1 mole of water contains 2 moles of hydrogen. And let's convert moles of hydrogen to grams of hydrogen. And 1 mole is 1.01. And when I do that, I get 2.07 grams of hydrogen. So because all of that hydrogen, if 2.07 grams of that hydrogen is in water, that must mean that this MTBE is also 2.07 grams of hydrogen. I got hydrogen, I got carbon. How much oxygen does this contain? Well, if the whole sample is 5.078 grams, we could figure out how much oxygen is in there just because I have these two values now. So 15.078 grams of MTBE minus 10.27 grams of carbon minus 2.07 grams of hydrogen. Subtract those guys, you should find that 2.74 grams of MTBE is oxygen. There's all the values you need to find the formula, because I know what mass of each element makes up that unknown hydrocarbon. So, knowing each of these, I'm going to highlight this. I know this, I know this, I know this. Let's go ahead and find the empirical formula. I'm going to set up my columns here. So I have carbon, hydrogen, and oxygen. We don't have percents here, and you don't need percents. I'm just going to use these masses because the masses work as well. So, and again, I just don't have to do that one step of converting percents to grams. I could just use grams straight away. 2.07 and 2.74. I'm going to do this off camera. You can go ahead and determine the empirical formula for this using those steps and stop this video and see if you get the answer that matches mine. There's the values that we get. 11.99 is practically 12. So my empirical formula is C5H12O. So this is empirical. Which I think is half the question here. So what is the molecular for? Oh, it's not even asking that, but I do need to determine the empirical. I do need to determine the molecular from the empirical. So the molecular mass is found to be this right here. All right, well, I have my empirical formula. The molar mass of the empirical is 88.17. Guess what? The molecular formula is 88.15, pretty darn close, right? So you could show a little work for that if you wanted to, but if I take that 88.15, which is the molar mass of the molecular, divided by this, I practically get 1, right? So, again, I did that. What the heck? So you get 1. That must mean that the empirical formula and molecular formula is the same. So let's write here C5H12O is also the molecular formula. Let's insert a little text box here and, not a vertical one. So we can make a little statement there as to what was going on. So let's see. Question is asking, what is the molecular formula of MTBE? We're going to say because of the empirical formula is equal to the molar mass of the molecular formula. The molecular formula is also C5H12O. So like I said, this is really putting it all together, right? Would I expect you to do a sample problem like this tomorrow? No, right? But I want you to understand the general idea of putting everything together that we've done so far in this type of real life problem. How do we determine the formulas for these hydrocarbons? And this is one way that we do that using everything we've learned so far in Unit 1. Of course, if you have any questions, please make notes in your note packet. Write these down for me, or write them down for me and ask me in class the next time you see me. Otherwise, I will see you in the next video, which is actually a review all about limiting and excess reagents. So that should be a little bit easier for you than this stuff here. I will see you then. Bye.